let's talk about stress in an engineering sense. So stress is basically the forces inside the material is related to the internal forces, to the internal forces of a material. Yeah, so basically stress is related to whether a piece of metal fails or not. So stress is related to the internal forces. So stress, there's going to be stress here. We're going to use the Greek little letter for S for stress, equals the force applied, so it's going to be force, and that's going to have a unit of newtons, over the area, which is going, and this is going to be cross-sectional area, cross-section, and that's going to be measured in meters squared. So the unit for stress is either going to be newtons per meter squared or pascals. You will see both units of measurement. They both exist happily in the world. So often what we want to know is the yield stress. If you look up on data information sheets, that's the stress at which the piece of metal, when you bend it, won't come back to its original shape. And we also know the ultimate tensile strength, which is the stress at which the piece of metal fails. So these are two very important pieces of information. So if you can work out the stress, you can work out how close to failure your piece of metal is. And also later on you can use it to see how much it's going to stretch. So let's do an example. A steel cable, diameter equals 12 millimeters, so has a 1500 kg load hanging from it. Load. What is the stress? So how can we do this? We draw a picture. So we draw, here's our cable, not to scale, and on the end we've got our load, whatever that may be, 1500 kg. So we know the stress is equal to force over area. So do we know the force? No. Can we work it out? Well, the force is going to equal, just going to be the gravitational force, so that's going to be mass times gravity, which is equal to 1500 kg, and for today we're going to use 10 meters per second squared for the gravity. If you use 9.8, feel free, but this just allows me to do it in my head. 15,000 newtons, so we know the force is equal to 15,000 newtons. And what's the cross-sectional area? Well, the cross-sectional area is, so if we have the load acting this way, the cross-sectional area is, if I cut it this way, what's the area of steel there? And the area is going to equal the area of a circle, in this case, is equal to pi r squared, which is the physics way of doing it. Or if you're in engineering, it's also equal to pi over 4 diameter squared. So you'll often use this in physics, you'll usually use this one in engineering. So the area is equal to pi over 4 times, if in doubt go back to meters, 0.012 meters squared. Calculator time, pi divided by 4 times 0.012 squared equals 113.1 times 10 to the negative 6 meters squared. Now what we do, so we just feed these numbers in, so equals 15,000 newtons over 113.1 times 10 to the negative 6 meters squared equals, again calculate time, 15,000 divided by 113.1 equals 600,000 units per square metre, which we can write that as equal to 132,600 pascals, or we can write it as 132.6 megapascals. So often in engineering you will see these figures given in megapascals, gigapascals, etc. Now the question is, does this answer seem reasonable? And yeah, it does. If you're dealing with metals, then the stresses will often be in hundreds of megapascals. For example, a lot of alloys of aluminium give way at about 280 megapascals. Steels will give way at much higher ratings. So 132.6 megapascals is perfectly fine. So what we do is we find out the load, convert it into newtons, we then say it's going this way, we cut a section across there, what's the area across there? That's going to be the area we stick under there, divide that by that, gives the stress.